Have you ever wondered why you can press your hand against a wall as hard as you like, yet not even the tip of your finger slips through? It feels so obvious that we almost never question it. Walls are solid. Hands are solid. Of course, one cannot pass through the other. But if you zoom into your hand 1,000,000 times, then 1,000,000,000, then 1,000,000,000,000, something astonishing happens. The solid flesh of your hand disappears. The atoms that seemed tightly packed begin to spread apart, revealing enormous empty spaces. Their nuclei become tiny points surrounded by clouds of electrons. Keep zooming, and those clouds themselves begin to lose their familiar appearance. What looked like tiny balls orbiting a nucleus was never an accurate picture. Instead, matter dissolves into strange quantum waves, probability distributions, and invisible fields stretching throughout space. Now look at the wall. The same thing happens. Its atoms are also almost entirely empty space. And suddenly the question becomes impossible to ignore. If both your hand and the wall are made almost entirely of empty space, why don't they simply pass through one another? Why doesn't your hand sink into the table while you're reading this? Why doesn't the Earth drift effortlessly through the sun? Why don't stars collapse into featureless points? Why don't entire galaxies simply dissolve into one another when they collide? The answer is one of the most beautiful discoveries in all of physics. It begins with an ordinary touch between your fingertips and a wooden table, but it ends in a place few people ever imagine, a world where identity itself becomes a law of nature.
Where no two electrons in the universe are allowed to share the same quantum existence, where invisible mathematical rules determine the architecture of every atom, every mountain, every planet, every star, and perhaps every living creature that has ever existed. Without this hidden rule, chemistry would vanish. The periodic table would disappear. The sun would not shine as it does today. White dwarf stars could never exist. Neutron stars would collapse long before we ever observed them. Planets would never become solid worlds. Even your own body could not hold its shape for a fraction of a second. Tonight, we are going to uncover one of the deepest reasons reality has structure at all. And by the end, you may discover that the greatest mystery isn't why your hand cannot pass through a wall. The greater mystery is why the universe chose these strange rules instead of countless other possibilities. For thousands of years, humans believed that solid objects were exactly what they appeared to be. A rock looked solid because it was solid.
A tree trunk resisted your hand because it was filled with continuous matter. This seemed perfectly reasonable. After all, every experience in daily life reinforced the same conclusion. You could lean against a wall. You could sit on a chair. You could build cities from stone. Nothing passed effortlessly through anything else. To ancient philosophers, this suggested that matter filled space continuously. There was no deeper mystery. But there were hints that reality might be stranger. Around the 5th century BCE, two Greek thinkers, Leucippus and later Democritus, proposed an extraordinary idea. They imagined that all matter might be made from unimaginably tiny, indivisible particles, which they called atoms, from the Greek word atomos, meaning uncuttable. It was an astonishing leap of imagination.
They had no microscopes, no experiments, no mathematics capable of testing the idea, only reasoning. They argued that if you kept cutting a piece of wood into smaller and smaller pieces, eventually you must reach something that could not be divided further. Ironically, they were both right and wrong. Matter is indeed built from atoms, but atoms are not indivisible. More than 2,000 years later, modern physics would reveal that atoms themselves contain nuclei, electrons, quarks, gluons, and perhaps even deeper layers that we still do not understand. Yet the boldness of Democritus's idea deserves admiration. Long before science had the tools to investigate nature, he imagined that the visible world might hide an invisible architecture. Centuries passed. Then, in the early 19th century, John Dalton transformed the philosophical idea of atoms into a scientific theory. Dalton noticed that chemical reactions followed precise numerical patterns. Hydrogen and oxygen always combined in fixed ratios to produce water. Carbon and oxygen formed different compounds only in specific proportions. These regularities suggested that matter was not continuous after all. It behaved as though it consisted of tiny, discrete building blocks. Dalton's atomic theory became one of the foundations of modern chemistry, but nobody knew what an atom actually looked like. For decades, scientists imagined atoms as tiny, hard spheres.
Simple, solid, featureless. Once again, reality was preparing a surprise. In 1897, J.J. Thomson discovered the electron. It was the first indication that atoms contained smaller components. Suddenly, atoms were no longer indivisible. They possessed internal structure. Thomson imagined electrons embedded inside positive matter like raisins inside a pudding. It seemed reasonable, until another experiment shattered that picture completely. In 1909, Ernest Rutherford, together with Hans Geiger and Ernest Marsden, performed what has become one of the most famous experiments in scientific history. They fired alpha particles toward an incredibly thin sheet of gold. According to the existing atomic model, the particles should pass almost straight through. Most did, but a few bounced backward. Rutherford later remarked that it was almost as incredible as firing a cannonball at tissue paper and having it rebound toward you. The conclusion was revolutionary. Almost all the mass of an atom was concentrated inside an incredibly tiny nucleus. Everything else was mostly empty space. Imagine placing a marble at the center of a giant sports stadium. That marble represents the nucleus. The outer seats represent where electrons are most likely to be found. Everything between them is almost entirely empty. Different analogies give slightly different scales, but they all communicate the same astonishing fact. Atoms are overwhelmingly empty. The objects surrounding you, the floor beneath your feet, the phone in your hand, the chair you're sitting on, are built almost entirely from emptiness. That realization alone changes the way you see reality. The human body contains roughly 7 octillion atoms. If every atom were compressed until all empty space vanished, your entire body would become smaller than a grain of dust. The density would be extraordinary. Matter would no longer resemble anything familiar. Yet despite being mostly empty, atoms somehow create materials stronger than steel, harder than diamond, and mountains capable of standing for hundreds of millions of years. How? At first glance, the answer seems obvious. Perhaps atoms collide like tiny billiard balls. Maybe their nuclei simply crash into each other. But physics quickly reveals that this explanation cannot work. The nucleus occupies only an incredibly small fraction of the atom's volume. If atoms behaved like miniature solar systems, direct collisions between nuclei would be extraordinarily rare. Most of the apparent volume of every object would simply overlap with another. Your hand should slide effortlessly through the table. The Earth should pass through the floor beneath it. Entire planets could drift through one another like ghosts. Yet reality stubbornly refuses to behave that way. Something invisible stops the overlap long before nuclei ever come close. Understanding that invisible barrier became one of the greatest scientific journeys of the 20th century. At first, physicists suspected electricity alone might explain everything. After all, electrons carry negative electric charge. Like charges repel. Perhaps the electrons surrounding your hand repel the electrons surrounding the table. That seems reasonable. In fact, electromagnetic forces do play an essential role. Whenever two atoms approach one another, their electric fields begin interacting long before their nuclei touch. The electromagnetic interaction is described with extraordinary precision by James Clerk Maxwell's equations in classical physics, and later by quantum electrodynamics, one of the most accurate scientific theories ever developed. But here's the surprise.
electrostatic repulsion alone is not enough. If electromagnetism were the complete explanation, many features of matter simply would not exist as they do. Calculations fail, atomic structures become unstable, chemistry loses its remarkable order. Scientists gradually realized that another principle, far stranger than electric charge, was quietly shaping reality beneath everything else. It wasn't another force. It wasn't another particle. It wasn't something you could switch on or off. It was a rule so fundamental that every electron in the observable universe obeys without exception. A rule that has never once been observed to fail. And remarkably, this rule has nothing to do with two electrons pushing each other away. Instead, it has everything to do with who they are. To understand why, we first have to abandon one of the oldest intuitions humans have ever had: the idea that particles are tiny little objects moving through empty space. Because at the deepest level we currently know, an electron is nothing like a miniature planet orbiting a miniature sun. In fact, asking exactly where an electron is turns out to be one of the most difficult questions in all of science. To understand why atoms refuse to occupy the same space, we first have to abandon one of the oldest pictures in science. For almost a century after Rutherford discovered the atomic nucleus, textbooks continued drawing electrons as tiny balls orbiting a nucleus like planets around the sun. It was a useful picture. It was also fundamentally wrong. Nature had already given physicists clues that electrons could not possibly behave like miniature planets. According to Maxwell's theory of electromagnetism, an accelerating electric charge continuously radiates electromagnetic energy. This is not merely an approximation. It follows directly from Maxwell's equations. Any charged particle moving in a curved path should emit electromagnetic radiation. An electron moving in a circular orbit is accelerating continuously because its velocity is constantly changing direction. If Rutherford's planetary atom were literally correct, every orbiting electron should radiate energy every second. As it lost energy, its orbit would shrink. Within roughly 10 to the minus 11 seconds, the electron should spiral into the nucleus. Every atom in the universe should destroy itself almost instantly. Yet atoms survive for billions of years. Every mountain, every ocean, every DNA molecule around you is silent evidence that classical physics has reached its limit. This was one of the major crises of 20th century physics. Nature was telling us something profound. Electrons are not tiny planets. But if they are not particles moving in orbits, what exactly are they? The first major clue came from an extraordinary proposal made by Louis de Broglie in 1924. Until then, light itself had become deeply mysterious. For centuries, Isaac Newton argued that light consisted of particles. Later, experiments by Thomas Young and Augustin Fresnel overwhelmingly demonstrated that light behaves like a wave. Then came Max Planck and Albert Einstein, showing that light sometimes behaves as localized packets of energy, photons. Light possessed a dual personality, sometimes wave, sometimes particle. De Broglie made an astonishing leap. Instead of asking why light behaves like matter, he asked why matter shouldn't behave like light. Suppose every particle possesses an associated wavelength, not metaphorically, literally. He proposed the remarkably simple relation lambda equals h over p, where h is Planck's constant and p is momentum. This tiny equation transformed physics forever. Large objects have enormous momentum. Their wavelengths become almost unimaginably small. A baseball, therefore, behaves almost perfectly like a classical object. But electrons possess extremely small momentum. Their wavelengths become comparable to atomic dimensions. Inside atoms, electrons are no longer tiny balls. They become waves. This prediction sounded almost absurd. Yet only a few years later, Clinton Davison and Lester Germer in the United States, and independently George Paget Thomson in Britain, demonstrated electron diffraction. Electrons passing through crystal lattices produced interference patterns, exactly what waves should produce, not what tiny billiard balls should produce. The evidence was overwhelming. Electrons interfere. Electrons diffract. Electrons spread. Electrons behave according to wave mechanics. This was not philosophical speculation, it was experimentally verified. Suddenly, the atom looked completely different. Instead of imagining electrons orbiting the nucleus, physicists now had to describe standing matter waves surrounding it. And here another extraordinary question appeared. A wave must be a wave of something. Water waves are disturbances in water. Sound waves are disturbances in air. Electromagnetic waves are oscillations of electric and magnetic fields. But what exactly is waving when an electron behaves as a wave? Even today, that question remains surprisingly subtle. In quantum mechanics, the mathematical object describing an electron is called the wave function, usually written as psi of r, t. This symbol appears innocent. It may be the most misunderstood symbol in science. The wave function is not simply a physical ripple moving through empty space, nor is it merely a probability cloud. Strictly speaking, the wave function is a complex-valued mathematical object whose squared magnitude, modulus of psi squared, gives the probability density of finding the electron during measurement. This interpretation was proposed by Max Born in 1926. It changed physics permanently. Before Born, physicists hoped the wave itself literally was the electron. Born suggested something much stranger. The wave evolves continuously according to deterministic mathematics, yet measurements reveal only probabilities. Nature itself appears fundamentally statistical. This idea disturbed many physicists. Einstein famously objected, "God does not play dice." Bohr replied that perhaps it was not our place to tell nature how it should behave. That debate continues philosophically even today. But experimentally, quantum mechanics has survived every precision test ever devised. Now notice something remarkable. Suppose two electrons approach each other. Classically, you imagine two tiny spheres moving through space. Quantum mechanically, there are no tiny spheres. There are two overlapping wave functions, two probability amplitudes, two quantum spates. Already, the question why can't they overlap begins changing into a much deeper question. Can two identical quantum wave functions occupy exactly the same quantum state? The answer turns out to be no. But before we discover why, we need another revolutionary equation. In 1926, Erwin Schrödinger asked a question almost nobody else thought to ask. If electrons behave like waves, what equation governs those waves? For water waves, there exists a wave equation. For sound waves, another. For electromagnetic radiation, Maxwell's equations. Matter waves must also obey a fundamental equation. After months of intense work, inspired partly by de Broglie's ideas and partly by Hamiltonian mechanics, Schrödinger arrived at what is now one of the most important equations ever written, the time-dependent Schrödinger equation. It predicts how every non-relativistic quantum system evolves. Unlike Newton's laws, which calculate trajectories, Schrödinger's equation evolves probability amplitudes. Instead of asking, where is the electron, it asks, how does the entire wave function evolve through time? This change seems almost linguistic. It is actually a complete redefinition of physical reality. Inside a hydrogen atom, the electron is no longer moving along a hidden orbit waiting to be discovered. Rather, the atom exists in a stationary quantum state. These are the familiar s, p, d, and f orbitals taught in chemistry. But even those textbook pictures can be misleading. Those beautiful cloud-like orbitals are not places where electrons travel. They are solutions of Schrödinger's equation. Each orbital represents one allowed standing wave configuration. Much like a vibrating violin string cannot vibrate with arbitrary shapes, the electron wave surrounding a nucleus can exist only in specific quantized patterns. The atom itself behaves remarkably like a three-dimensional resonant cavity. Only certain wave patterns fit. Everything else simply cannot exist. This explains why atoms possess discrete energy levels. It explains atomic spectra. It explains why hydrogen emits very specific wavelengths. It explains why chemistry is quantized. The atom is not built from little planets. It is built from standing quantum waves. Yet even this astonishing picture remains incomplete. Because if quantum mechanics ended here, nothing would prevent every electron in the universe from collapsing into the lowest energy orbital surrounding every nucleus. Imagine hydrogen. The lowest energy orbital, the 1s orbital, is the most stable state available. If electrons behaved independently, every electron would simply occupy that single state. Every atom heavier than hydrogen would become impossible. Carbon could never exist. Oxygen would disappear. Iron would never form inside stars. The periodic table would collapse into absurd simplicity. The universe would consist almost entirely of identical hydrogen-like atoms. Life would be mathematically impossible. Clearly, nature imposes another restriction, one so deep that Schrödinger's equation alone cannot explain it. Something distinguishes electrons from photons. Something prevents identical electrons from sharing the same quantum state. Something so fundamental that it determines the size of every atom, the rigidity of every crystal, the structure of every molecule, the existence of white dwarf stars, and ultimately whether galaxies contain planets capable of supporting life. That mysterious rule was uncovered by a 24-year-old physicist in 1925. His name was Wolfgang Pauli, and what he discovered was not another force of nature. It was something far stranger, a law of identity itself. Wolfgang Pauli did not begin by trying to explain why your hand cannot pass through a table. In fact, that question was nowhere in his mind. His original problem was much narrower: atomic spectra. When physicists observed the light emitted by atoms, they found thousands of spectral lines that refused to obey the existing quantum theory. Schrödinger's equation explained much, but not everything. Certain electronic configurations appeared to violate every expectation. The mathematics seemed incomplete. Pauli became obsessed with finding the missing rule. For months, he worked through increasingly complicated calculations. Finally, in 1925, he proposed what initially looked almost absurd. No two electrons inside the same atom can possess an identical set of quantum numbers. It sounded like an accounting rule rather than a law of nature. Yet this single statement reconstructed the entire periodic table. Every chemical element suddenly made sense. But almost immediately, physicists asked a much deeper question: why? Why should nature care whether two electrons share identical quantum numbers? Nothing in Newton's laws suggests such a restriction. Nothing in Maxwell's equations requires it. Even Schrödinger's equation by itself does not forbid identical particles from occupying exactly the same quantum state. The answer emerged only after physicists realized that they had been making another hidden assumption. They had been unconsciously treated identical particles as though they possessed invisible labels: electron number 1, electron number 2, electron number 3. Nature refuses to do this. Imagine placing two perfectly identical electrons into an experiment. After a brief interaction, they scatter apart. Now ask yourself a seemingly innocent question: which outgoing electron is the first one? Which is the second? The question itself has no physical meaning. There exists no experiment capable of identifying them. No hidden serial numbers, no microscopic fingerprints, no secret internal color, no secret identifier. Electrons are not merely similar, they are fundamentally indistinguishable. This sounds almost philosophical. It is actually one of the most rigorously tested properties in modern physics. Every electron possesses exactly the same rest mass, exactly the same electric charge, exactly the same intrinsic spin, exactly the same magnetic moment, exactly the same interaction strength with electromagnetic fields. If tomorrow we discovered even one electron whose charge differed by 1 part in a trillion, quantum electrodynamics would collapse. Instead, every experiment has found complete identity. This is astonishing. Imagine manufacturing 10 trillion tennis balls. Each would differ slightly. Different scratches, different masses, different molecular arrangements. Nature has produced roughly 10 to the 80 electrons throughout the observable universe. Not one has ever been observed to differ from another. Modern quantum field theory explains this beautifully. There are not billions of separate electrons. There exists one electron field filling the entire universe. Every electron is simply an excitation of that single field. Exactly, as every photon is an excitation of the electromagnetic field. Think carefully about what this means. When a photon is created inside a distant galaxy billions of light years away, and another photon is emitted by the screen you're watching now, they are not separate species of photons. Both are excitations of one universal field. The same is true for electrons. Your body does not contain unique personal electrons. The electrons flowing through your brain, your heart, and your fingertips are indistinguishable excitations of the same underlying quantum field that stretches across intergalactic space. Identity is not manufactured. Identity comes from the field itself. Already, our picture of reality has changed dramatically. Matter is no longer made from tiny, independent objects. Matter is composed of localized excitations of continuous quantum fields. This idea became the foundation of quantum field theory, developed by physicists including Paul Dirac, Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and later expanded into the Standard Model. But indistinguishability alone does not explain exclusion. Something else must happen mathematically. Suppose two identical electrons occupy positions R1 and R2. Quantum mechanics describes the pair using a single joint wave function, psi of R1, R2. Now exchange the particles. Nothing observable has changed. The electrons are identical. Nature therefore demands that every measurable prediction remains unchanged. But quantum mechanics allows only two mathematical possibilities. Either psi of R1, R2 equals plus psi of R2, R1, or psi of R1, R2 equals minus psi of R2, R1. There is no third option. Particles described by the positive sign are called bosons. Particles described by the negative sign are fermions. Electrons belong to the second category. Now comes the crucial step. Suppose two identical electrons attempt to occupy exactly the same quantum state. Mathematically, R1 equals R2. Substituting this into the antisymmetric relation gives psi equals minus psi. Only one mathematical solution exists. Psi equals 0. Not approximately 0, exactly 0. The probability of finding two identical fermions occupying precisely the same quantum state completely vanishes. Nature has erased the possibility before any force ever acts. This is the Pauli exclusion principle expressed in its deepest mathematical form. Notice something extraordinary. No physical collision occurs. No repulsive force suddenly switches on. No tiny springs push electrons apart. The forbidden configuration simply possesses 0 probability amplitude. The universe refuses to realize it. This distinction is subtle. It changes everything. When you press your hand against a table, people often imagine billions of electrons actively repelling each other like compressed springs. That picture is incomplete. The dominant resistance of ordinary matter is not a mechanical force in the everyday sense. It is a quantum restriction on the allowed states available to electrons. As electron clouds begin overlapping, fewer and fewer quantum states remain available. Electrons are forced into higher energy states. That increase in quantum kinetic energy manifests macroscopically as an enormous restoring force. Matter resists compression because compressing it requires rearranging electrons into increasingly energetic quantum configurations. The resistance originates from quantum statistics as much as electromagnetism. This distinction is one of the reasons condensed matter physics became one of the richest areas of modern science. Even today, researchers investigate quantum materials whose collective electron behavior produces superconductivity, topological phases, quantum Hall states, and entirely new forms of matter. All emerge from the statistical behavior of countless indistinguishable fermions. To appreciate the scale of this effect, imagine trying to compress a simple metal. At first, the atomic lattice deforms elastically. Increase the pressure further. Atoms move closer. Electron wave functions begin overlapping more strongly. Available quantum states become crowded. According to Fermi-Dirac statistics, electrons fill available energy levels one by one, beginning with the lowest. Unlike photons, which can pile into a single state without limit, as happens inside a laser, electrons cannot. Each additional electron must occupy a new quantum state with slightly higher momentum. This creates what physicists call the Fermi sea. At absolute zero, electrons do not all sit motionless. Instead, they occupy every available state, from the lowest energy upward until reaching the Fermi energy. Even at zero temperature, enormous microscopic motion remains. This surprises many people. We usually associate motion with heat. Quantum mechanics disagrees. Remove every possible unit of thermal energy. Cool a metal until it approaches absolute zero. Its conduction electrons still possess substantial momentum, not because of temperature, because the exclusion principle demands it. This is called degeneracy. The word has nothing to do with disorder. It describes systems whose behavior is dominated by quantum statistics rather than thermal motion. Already we can glimpse an astonishing consequence. The solidity of matter around you is not merely electromagnetic. It is thermodynamic. It is statistical. It is quantum mechanical. It is the inevitable consequence of antisymmetric many-body wave functions. Every chair, every mountain, every diamond, every cell membrane, every protein folded inside your body owes its stability to a rule that says identical fermions cannot occupy identical quantum states. Now imagine removing that rule. Carbon atoms lose their electronic shell structure. Chemical bonds disappear. The periodic table ceases to exist. Metals become meaningless. Semiconductors vanish. DNA never forms. Stars ignite differently. Planetary interiors collapse. Even the distinction between solids and liquids largely disappears. Reality itself becomes almost unrecognizable. But perhaps the most astonishing consequences do not occur inside atoms. They occur inside dying stars. When nuclear fusion finally stops, gravity begins winning. A star starts collapsing inward under its own immense weight. Every second, gravity squeezes matter harder than anything humans can reproduce on Earth. Ordinary chemical forces fail almost immediately. Atomic bonds shatter, molecules disappear. Eventually, even individual atoms are crushed. At these unimaginable densities, one might expect gravity to continue compressing matter indefinitely. Instead, the same quantum rule preventing your hand from passing through a table rises to cosmic importance. The Pauli exclusion principle begins resisting the collapse of an entire star. A law discovered while studying tiny atomic spectra suddenly determines the fate of objects larger than Earth. And this raises one of the most remarkable questions in astrophysics. Can a simple quantum rule really hold back the gravity of a dead star containing roughly the mass of our Sun? As unbelievable as it sounds, the answer is yes. And understanding how takes us into one of the greatest triumphs of 20th century physics. References: W. Pauli in Über den Zusammenhang des Abschlusses der Elektronengruppen, 1925. P. A. M. Dirac, The Principles of Quantum Mechanics, in 1930. There is another subtle misconception that almost everyone, including many science communicators, repeats when explaining why objects cannot pass through one another. They say, electrons repel each other because they have the same electric charge. The statement is true, but it is not the whole truth. In fact, if you asked a condensed matter physicist what makes a diamond rigid or why ordinary solids resist compression, many would immediately point out that electrostatic repulsion alone cannot account for the observed mechanical properties of matter. Why? Because quantum mechanics refuses to let us separate electricity from statistics. Imagine slowly bringing two hydrogen atoms toward one another. When they are very far apart, each electron is comfortably localized around its own proton. Their wave functions barely overlap. Electromagnetic interaction is weak. Everything behaves almost independently. Now begin decreasing the separation. The first thing that changes is not the nuclei, not even the electrons as particles. It is the wave function describing the entire system. This is one of the hardest conceptual shifts in quantum mechanics. Nature does not first calculate where every electron is and then decide how strongly they repel. Instead, nature determines which many particle wave functions are mathematically allowed. Only afterward do measurable quantities emerge. This means the true object in quantum mechanics is not an electron, it is the entire quantum state. That distinction is enormous. Because once electron wave functions begin overlapping, they stop behaving like independent entities. They become a single antisymmetric many-body wave function. This mathematical object may involve billions upon billions of interacting particles simultaneously. Already, we have left behind the comforting world of individual atoms. We are entering the domain of many-body quantum mechanics, one of the most difficult subjects in modern theoretical physics. In this framework, something remarkable happens. Suppose you force two identical electrons closer together. Because the total wave function must remain antisymmetric under particle exchange, P R1 R2 equals minus P R2 R1, the spatial part of the wave function develops curvature. That curvature is not merely a mathematical curiosity. Curvature in a wave function carries energy. This follows directly from Schrödinger's equation. The kinetic energy operator, T hat, equals minus h bar squared over 2m times del squared, depends on the second spatial derivative of the wave function. Notice something profound. There is no force term here, nothing resembling Coulomb repulsion, nothing pushing particles apart. Yet increasing localization inevitably increases the wave function's curvature, and increasing curvature raises kinetic energy. This is one of the strangest ideas in quantum mechanics. Particles can resist compression without any classical force acting between them. The resistance emerges purely from geometry in Hilbert space. Think carefully about what this means. The universe is not merely resisting compression because electrons dislike each other's electric charge. It is resisting compression because certain wave functions become increasingly expensive in terms of energy to construct. Reality chooses the configuration requiring the lowest total energy, and those configurations naturally keep electrons separated. In condensed matter theory, this behavior is sometimes described as exchange energy. The exchange interaction is not a new fundamental force. It originates entirely from anti-symmetrizing the many-electron wave function. Yet it behaves so much like a force that atoms arrange themselves into crystal lattices, magnetic domains form inside iron, and chemical bonds acquire their remarkable stability. One mathematical symmetry produces an enormous range of physical phenomena. This is one of physics's recurring themes. Symmetry determines possibility. Whenever physicists discover a deeper symmetry, they usually discover an entirely new layer of reality. Gauge symmetry gives rise to electromagnetism. Lorentz symmetry shapes relativity. Rotational symmetry produces angular momentum conservation. Translational symmetry produces momentum conservation. Permutation symmetry gives us quantum statistics. And quantum statistics determines the architecture of matter itself. This connection between symmetry and physical law became one of the greatest intellectual achievements of 20th century physics. The mathematician Emmy Noether proved something astonishing in 1915. Every continuous symmetry corresponds to a conserved quantity. Her theorem transformed theoretical physics forever. Although particle exchange belongs to a discrete symmetry rather than a continuous one, the broader lesson remains the same. Nature appears to organize itself through mathematical invariance. The universe is less like a machine, more like a mathematical structure. The further physicists probe reality, the less they encounter tiny mechanical objects. Instead, they encounter symmetries, operators, representations, fields, groups, topology, information. Some theoretical physicists, including Roger Penrose and others, have even argued that mathematics may not merely describe reality, it may constitute reality's deepest language. And nowhere is that more striking than in the behavior of identical particles. Now let us ask an even stranger question. Why are electrons fermions at all? Why do electrons obey antisymmetric statistics while photons happily pile into the same state? Why can trillions of photons occupy one laser mode, yet two electrons refuse to share a single quantum state? For decades, this appeared to be another arbitrary rule. Then, relativistic quantum field theory uncovered something extraordinary. The answer lies in space-time. More specifically, in how quantum fields transform under Lorentz transformations. Particles possessing half-integer intrinsic spin, 1/2, 3/2, 5/2, must obey Fermi-Dirac statistics. Particles possessing integer spin, 0, 1, 2, must obey Bose-Einstein statistics. This relationship is known as the spin statistics theorem. It is one of the deepest theorems in all of theoretical physics. Unlike the Schrödinger equation, which can be motivated from wave mechanics, the spin statistics theorem requires the machinery of relativistic quantum field theory. Its proof depends on Lorentz invariance, microcausality, positive energy, and the requirement that information cannot propagate faster than light. If you attempt to construct a relativistic universe where spin half-particles behave like bosons, the mathematics breaks. Probability becomes negative. Causality fails. The vacuum becomes unstable. The theory ceases to describe a physically consistent universe. In other words, electrons do not obey the Pauli exclusion principle because nature arbitrarily decided they should. They obey it because a relativistic quantum universe appears incapable of existing otherwise. That statement is breathtaking. The solidity of your chair depends upon the causal structure of space-time itself. Your inability to push your hand through a wall is connected, through several layers of theory, to Lorentz symmetry and the quantum structure of the vacuum. Few people realize just how deep this rabbit hole goes. And the rabbit hole is still not finished, because we have quietly ignored something else. Throughout this discussion, we have treated electrons as though they possessed definite positions, but according to quantum field theory, position itself is not fundamental. Fields are fundamental. Particles are secondary. This completely changes our picture of reality. Imagine removing every electron from the observable universe. The electron field would still remain. It would still fill every cubic centimeter of intergalactic space. It would still obey the Dirac equation. It would still fluctuate according to quantum uncertainty. The field itself never disappears. This is profoundly different from classical intuition. Objects are no longer primary. The stage itself has become the actor. Matter becomes patterns. Patterns become fields. Fields become the fundamental entities from which everything observable emerges. If that picture is correct, then perhaps the real question was never, why can't atoms pass through each other? Perhaps the deeper question is this: why does the universe allow only certain field configurations to exist while forbidding others completely? That question carries us far beyond chemistry, far beyond atoms, and directly toward the deepest frontier of modern theoretical physics, where quantum field theory, gravity, black holes, and perhaps an eventual theory of quantum gravity must finally meet. Because when gravity becomes strong enough, Even the astonishing power of the Pauli exclusion principle eventually reaches its limit. As gravity continues to increase, something extraordinary begins to happen. The familiar picture of matter quietly disappears. The atoms that once defined chemistry no longer exist. There are no molecules, no crystals, no metals, no chemical bonds. Temperature has become so enormous and density so extreme that every electron has been stripped away from every nucleus. Matter has entered the plasma state. To an observer standing impossibly close, the distinction between the elements themselves is beginning to lose meaning. Yet gravity is only getting started. Inside the core of a dying star, the inward gravitational force is relentless. Every cubic centimeter contains more matter than entire mountains on Earth. The distance between neighboring nuclei shrinks from angstroms, about 10 to the negative 10 meters, to femtometers, roughly 10 to the negative 15 meters. 5 orders of magnitude vanish. Entire atomic structures are compressed until they cease to exist. Now something remarkable happens. The electrons no longer behave as individual particles moving around nuclei. Instead, they form what physicists call a degenerate Fermi gas. The word gas is misleading. This is nothing like the air in Earth's atmosphere. An ordinary gas is governed mainly by temperature. Molecules fly randomly, collide, exchange energy, and gradually spread out. A degenerate Fermi gas is governed almost entirely by quantum mechanics. Imagine an enormous concert hall with infinitely many rows of seats. Every seat represents one allowed quantum state. According to the Pauli exclusion principle, each seat can accommodate only one electron of a given spin orientation. As more and more electrons are added, the lowest seats fill first, then the next row, then the next. Eventually, even seats corresponding to extremely large momenta become occupied. Notice something subtle. No one has heated the system. No external engine has accelerated the electrons. Their enormous momenta arise simply because there are no lower energy quantum states left to occupy. This is perhaps one of the strangest forms of energy in nature. The energy exists not because something happened. It exists because the alternatives are forbidden. Quantum mechanics is dictating the architecture of phase space. To describe this quantitatively, physicists introduce the concept of Fermi momentum. Imagine drawing an abstract three-dimensional space, not ordinary space, but momentum space. Every possible momentum corresponds to one point. Electrons gradually fill this momentum space from the center outward, creating what is known as the Fermi sphere. Every state inside the sphere is occupied. Every state outside remains empty. At absolute zero, this sphere has an extremely sharp boundary. The momentum at that boundary is called the Fermi momentum, PF. Everything about the electron gas, its pressure, energy density, heat capacity, electrical conductivity, can be derived from this single quantity. This is one of the triumphs of quantum statistical mechanics. A macroscopic object containing roughly 10 to the 57th electrons can be understood by counting allowed quantum states. Physics repeatedly teaches the same lesson. Nature prefers counting possibilities over calculating trajectories. Now gravity attempts another compression. To squeeze the star further, electrons would need to move into quantum states beyond the Fermi surface. But those states possess increasingly larger momentum. And because relativistic energy grows rapidly with momentum, E squared equals P squared C squared plus M squared C to the fourth. Every additional compression demands an enormous increase in energy. That increase appears macroscopically as electron degeneracy pressure. It is crucial to understand what this pressure is and what it is not. It is not a force transmitted through contact. It is not electromagnetic repulsion. It is not thermal pressure generated by heat. Even if the star were cooled toward absolute zero, this pressure would remain. Electron degeneracy pressure is a manifestation of the available geometry of quantum states. In other words, the star is resisting collapse because quantum mechanics refuses to provide enough low-energy configurations. Gravity is fighting mathematics. For stars roughly comparable to the Sun, mathematics wins. The star stabilizes as a white dwarf. Imagine an object roughly the size of Earth containing almost the entire mass of the Sun. 1 teaspoon of its material would weigh several tons on Earth. Yet despite these unimaginable densities, the star survives because every electron is already occupying the lowest quantum state available to it. The discovery that quantum mechanics could support an entire star was astonishing enough. But in 1930, a 19-year-old student traveling by ship from India to England began asking an even more dangerous question. His name was Subrahmanyan Chandrasekhar. Using Fermi-Dirac statistics, special relativity, and stellar structure equations, Chandrasekhar calculated what would happen if the star became even more massive. As the density increased, the electrons would become increasingly relativistic. Eventually, the pressure and density relationship would change. Degeneracy pressure would continue increasing, but not fast enough. Gravity would begin catching up, then surpassing it. His calculations predicted something extraordinary. There exists a maximum mass beyond which no white dwarf can remain stable. Today, we call it the Chandrasekhar limit. Approximately 1.4 m solar, where m solar represents the Sun's mass. Above this limit, electron degeneracy pressure inevitably fails. When Chandrasekhar presented these results, one of the greatest astrophysicists of the age, Arthur Eddington, rejected them publicly. Eddington found the conclusion almost absurd. How could a perfectly respectable star simply continue collapsing forever? He believed nature must contain another mechanism that would prevent such an outcome. History proved Chandrasekhar correct. Decades later, observations of white dwarfs confirmed his calculations with remarkable precision. It was one of the greatest victories of theoretical astrophysics. Yet Chandrasekhar's work raised an even deeper question. If electron degeneracy pressure fails, what happens next? Gravity does not pause to reconsider. The collapse continues. Eventually, the pressure becomes so immense that electrons are literally pushed into protons. Through inverse beta decay, P plus E minus equals N plus nu E, protons capture electrons and become neutrons while emitting electron neutrinos. Matter undergoes a profound transformation. The particles responsible for chemistry disappear. The periodic table vanishes. Atoms no longer exist. The star becomes, for the first time in cosmic history, an object composed primarily of neutrons. Now the Pauli exclusion principle returns, but in a new disguise. Neutrons are also fermions. They also possess spin 1/2. They also obey antisymmetric wave functions. Another Fermi sea forms. Another degeneracy pressure emerges. Once again, gravity encounters a quantum barrier. A neutron star is born. This object pushes human intuition almost beyond breaking point. A sphere only about 20 kilometers across contains more mass than our Sun. Its density approaches that of an atomic nucleus. A sugar cube-sized piece would outweigh Mount Everest. Light bends dramatically around it. Time itself slows measurably in its gravitational field. Some neutron stars rotate hundreds of times every second, sweeping beams of radio emission across space like cosmic lighthouses. Others possess magnetic fields exceeding 10 to the 11 Tesla, strong enough to distort atomic structure itself. The vacuum surrounding them is no longer empty in the ordinary sense. Quantum electrodynamics predicts that even empty space begins responding to magnetic fields of such intensity. Virtual particle pairs become polarized. The vacuum acquires optical properties. In other words, space-time itself begins behaving like a physical medium. What began as the question, "Why can't my hand pass through a table?" has quietly carried us to objects where empty space behaves like a crystal, where time slows, where matter no longer consists of atoms, where quantum mechanics determines the destiny of entire stars. But gravity still has one final move. If the collapsing core exceeds roughly 2 to 3 solar masses, depending on the still uncertain equation of state of ultra-dense nuclear matter, even neutron degeneracy pressure fails. At that point, modern physics reaches one of its greatest frontiers. The very principle that built atoms, constructed chemistry, supported white dwarfs, and delayed the collapse of neutron stars can no longer halt gravity. The collapse continues toward a regime where general relativity predicts a singularity, but quantum mechanics insists our current description is incomplete. This is not merely a gap in knowledge, it is one of the greatest unsolved problems in science. The mathematics of Einstein and the mathematics of quantum field theory, each spectacularly successful in their own domain, refuse to merge under these extreme conditions. Somewhere inside that collapse, our understanding of reality reaches its present limit. And perhaps that is the deepest lesson hidden inside the simple act of touching a wall. The question was never really about solidity. It was about discovering that every ordinary experience is the visible surface of laws so profound they govern everything from the arrangement of electrons in a carbon atom to the birth of chemistry, the lives of stars, the structure of galaxies, and the boundaries of human knowledge itself. When you place your hand on a table, you are not feeling solid matter. You are feeling quantum mechanics enforcing a rule that has never once been observed to fail anywhere in the observable universe. A rule born from the symmetry of indistinguishable particles. A rule encoded into the fabric of quantum fields. A rule that determines whether the universe contains atoms instead of featureless plasma, planets instead of collapsing clouds, stars instead of singularities, and life instead of mathematical impossibility. And perhaps the most humbling realization is this. After a century of extraordinary discoveries, we still cannot answer the deepest question. Why does the universe possess these quantum rules at all? The Pauli exclusion principle can be derived from the spin statistics theorem within relativistic quantum field theory. The theorem follows from Lorentz invariance, locality, and quantum mechanics. But those assumptions themselves are not explained. They are accepted because every experiment confirms them. In other words, physics has revealed how the universe enforces this rule with astonishing precision. It has not yet revealed why reality is built on exactly these mathematical foundations and not others. Somewhere beyond quantum field theory, beyond general relativity, and perhaps beyond our current imagination, there may exist a deeper framework from which these rules emerge. Whether that framework is quantum gravity, string theory, loop quantum gravity, or something entirely unforeseen remains unknown. Until then, every time your hand rests effortlessly on a table, it serves as a quiet reminder that one of the deepest mysteries in the universe is not hidden inside a distant galaxy. It is happening beneath your fingertips, every fraction of every second.